One of the topics this week is going to be talking about radar. So I really thought I would just start by we'd look at some radar where there is something going on today. And today we have a little bit of precipitation down in western part of Texas. So this is radar from Lubbock, Texas. What you're seeing here is what I would call base reflectivity. Well, what does that mean? When a radar sends out a little pulse, it goes along one trajectory. The antenna actually rotates upward with time and then back down again and restarts the process. And all this while it's spinning around, doing it in 360 degrees. So a radar is actually looking at a volume of air. What you're seeing here is the lowest level of that volume of air and its reflectivity. As you approach, you can see the scale here. You get the yellows more intense, more the reds, thunderstorms even more intense, maybe into whites. Here is some heavier rain showers occurring south of Lubbock right now. We could loop this if you wanted to see it in motion, but I thought I would just show you different aspects. We talk about Doppler radar. What does Doppler radar mean? Well, Doppler radar means I can see velocity. I am seeing the velocity of these echoes. In other words, I'm looking at these precipitation particles here and I'm seeing their motion. So what is the motion currently in this as well? So let's take a look at base velocity, which is real-time velocity. Now, a particle moving perpendicular to the radar shows up as zero base velocity. So right along this little curve here is no wind. The radar doesn't think these particles are moving. So that means that the wind is actually blowing from southwest to northeast right through here, and more from the west to east at this higher elevation, because this is actually further and further away from the radar. It's sampling higher up. So it's getting more and more elevation, and it's actually seeing the wind at a higher elevation. So there's an actual turning with wind from the southwest to the west as you go up here. Kind of interesting to be able to see the velocities of these particles where they're moving. In this case, we're not too worried about thunderstorms or real small scale circulations, but we are getting to see some of the precip. So let's take a look at dual pole precipitation type. Dual pole is a means. We'll come back here in a second, maybe. But here is what dual pole radar really is. It used to be radar sent out a horizontal pulse. We could see it. That was it. Now it sends out a horizontal and a vertical. It has shape, two-dimensional shape. So it's able to pick out a shape of a raindrop, a two-dimensional shape, not three. And with that, it means I can identify maybe that, oh, that is a raindrop. That is hail. That is snow. So we use that by looking at differential reflectivity, how its reflectivity is changing. Here, for example, is hail. Before we had dual pole, this would be what I had. And yes, I would identify this as a likely hail signature. Now, with differential reflectivity, notice how you get this area that changes color. It's actually detecting that this is ice in here, not rain. So it's able to identify that to me, and I am able from that to say with 100% certainty there's hail here. So now, instead of just looking at, oh, there might be hail, I'm able to tell you, yes, there is hail. Now my job becomes, well, how big is that hail? That's another process that we've looked at. But yeah, all of that. And we can come back in here now, look at dual polarization, and there's other things we can do with it. One of the really cool things is we can tell exactly how high some of the precipitation, the ice area of precipitation is. In other words, when it changes from liquid to solid, there's going to be a change in this. So that was something I wanted to show you, but obviously we're not going to here. But I can show you over here a little bit with dual pole, where it shows precipitation type. Notice the precipitation type right now is pretty much snow because it's looking aloft, not looking at low levels. If it was down closer to the ground, we'd be differentiating more into the rain category. So let's take a look at this slide here a minute. Now that we've talked about radar and what that does for us, let's talk about how we get the clouds and the precipitation that this radar is really good at detecting. So water vapor is invisible. When you look out on a summer day and it is so humid out there, but you can still see there isn't a cloud in the sky, maybe in the morning, but there's a ton of water vapor in that air. That water vapor is, you can't see it. Not till it condenses can you see it. And there are some difficulties in why clouds form. Believe it or not, if the air was completely clean, we wouldn't see many clouds. Why is that? Well, water vapor is really, really, really tiny. Here's a kind of to scale depiction between a raindrop and a cloud droplet. Cloud droplets are really, really small. That means there is a very gradient of circle, very tight circle they have. When you get it that small, it means that water wants to evaporate easier than it does on a flat surface where we take relative humidities. So the 100% humidity that you see on a flat surface, when it's very, very small, like a tiny raindrop, all of a sudden you need 300, 400, 500% relative humidity to create that raindrop. So something else has to be happening to make that raindrop, and that's condensation nuclei. They can be dust, they can be salt from the ocean. All of these are things that can help a raindrop begin to form. What happens is that condensation nuclei literally dissolves. It creates a solution that allows that raindrop to hold in its condensed, its water. So now that we've got raindrops, they can begin to grow with time. And this condensation nuclei actually begins to create raindrops at right around to 100%, just a little bit less than that. So as the cloud droplet begins to grow, the curvature effect will become less, and it'll actually won't need that condensation nuclei as much. So these are really important for the smallest of the cloud droplets. Now, to get something to freeze in the atmosphere, you would think, oh, 32 degrees, it freezes, right? Well, again, these are little tiny droplets, so they don't freeze at 32 degrees. Matter of fact, they can get very, very cold before they even begin to freeze. If you didn't have anything, no ice forming nuclei in them, they could literally reach a point, what's called the Schaefer temperature. It's about minus 39 degrees Celsius. And that would be the first time that you would get any ice in these clouds. But again, we have, like dust, salt, some other particles that mix in with these little raindrops, and they allow them to freeze. So that is how ice now forms. Usually we're looking at about minus 10 Celsius or so. We start getting more ice. So when we're looking at clouds and you're seeing ice forming in it, and you can see that by the way the clouds look, we talked about that earlier, that level is above probably minus 5 to minus 10 Celsius. So you've actually gone below freezing where that part of the cloud is. So these very small droplets actually inhibit that kinetic energy. Oh yeah, what about precipitation? Well, how do we get rain or snow here on Earth? We know that gravity is always trying to pull those droplets down. However, there's friction. Going to learn about it, trying to hold those droplets up. So at some point, the droplet's going to get heavy enough that it is going to begin to move down, and it'll reach what is called terminal velocity, and that's as fast as it's going to fall, no matter how far it has to go. And there are two methods that form precipitation. One's called collision coalescence. It actually occurs more in the summertime around here. It's called a warm cloud process. What's that mean? Temperatures are above freezing in the cloud, and literally droplets grow by colliding with each other. Here is what you would actually, a depiction of that. One drop gets a little bit bigger and begins to drop down. Well, it bumps into another drop. Oh yeah, it absorbs that one. Gets a little bigger. Now it drops into a couple more drops. And as you can see, that gradually gets big enough that it becomes a raindrop. Now it's overcoming the friction of the air and it begins to fall to the ground. That's collision coalescence. You need a lot of moisture. Remember, the warmer the air is, the more moisture the air can hold. So temperatures above freezing require a lot of moisture in the air. The Bergeron-Findeisen effect, on the other hand, is what predominantly creates precipitation in our part of the world, in mid-latitudes. So the first thing that happens is you get these ice condensation nuclei that begin to create a snowflake. That snowflake, remember we learned last week that the saturation vapor pressure around ice is lower than it is around liquid. So if the pressure difference, higher pressure for the saturation vapor, is around the liquid, lower is around the ice, guess where that liquid is going to go? The water vapor is going to flow from those water particles into the ice crystals, making them grow. That's the key to the Bergeron-Findeisen effect. It gradually just basically means that those water droplets are turning into ice and the ice is growing. So, some precipitation never makes the ground. Why is that? Remember, the precipitation is falling through the air. If the air is very dry, say the desert Southwest, the precipitation is going to evaporate as it's falling. There are different types of precipitation. One is rain, which you're very familiar with. Drizzle is another one, which is very small droplets. And here's the snow. Guess what? Snow's all kinds of shapes. And what's interesting, I want you to notice something here. Notice this dendrite. And now notice these solid prisms. Which one do you think is going to accumulate more snow at your house? A shape like this or a shape like this? This has a lot more air holes in it, much bigger. Same amount of moisture is doing each of these. So, a key to forecasting snowfall is knowing what kind of snowfall you're going to get. Most snow is dendrite. But some are not. Some are more thin platelets. Maybe they're so cold that they're columns of ice, like this or there. Whatever. The difference in the amount of snow, say you had a ½ inch of liquid precip, and we'll say a 10-to-1 ratio of snow. That would mean 5 inches of snow. It's a dendrite. If, on the other hand, it's more in columns, that may be more 2 to 3 inches of snow. 2 to 3 inches might be fairly easy to deal with. 5 inches might begin some problems. You see the issues now in forecasting snowfall. So we want to know what kind of precipitation is falling, and part of that is what is falling. Most of the precipitation that originates in the cloud in our latitude is going to be snow. Now, we know temperatures vary with height. Normally they get colder, but sometimes warm air can come in aloft. As we know, warm air rises up over cold air. If that were to take place, it can melt that snow, turn it into liquid, and then if there's some cold air below it, maybe there's some sleet going to form, maybe there's going to be some freezing rain, or maybe it's warm enough all the way that it's going to be all rain. So now you can see this warm air aloft can influence the precipitation types. So here we have freezing rain. All right, so I talked about radar and all that to you earlier. So I think that's going to do what I want to discuss today. I hope you got something out of this. There are quite a few radar stations around the country, and they do have one really interesting depiction here that I did want to pop up. It's a tornado. And you'll notice that I talk about circulations. Well, right here is a circulation. Winds are going, you can literally see right next to each other in the opposite direction extremely fast. That's how we determine tornadoes are possible. We're looking for that circulation aloft. So, hope you got something out of all this. No, please don't hesitate to ask if you have any questions. And yeah, this week, try to see what kind of precipitation you're getting, or why is that cloud forming up there? Might be an interesting exercise.